Discuss the classical way of defining determinant of a matrix. In fact, for a square matrix. In 5.1, there is a discussion on rings. You already discussed rings in your degree classes. So we use the symbol K for a commutative ring. A commutative ring K is a ring whose multiplication is commutative. So in this rest of this chapter, we will consider K as a commutative ring with unity, and unity is denoted as 1. Example of such ring is MNF. This is set of all square matrices of order n, and this is a ring. It's a commutative ring. This is not commutative ring. This is a ring. It's a ring with identity or unity, and the identity element is in. So this is an example of a ring with identity, and we have but this is not commutative anyway. MNF is not commutative, but if you consider set of all real numbers under usual addition and multiplication, this form a commutative ring with identity. The identity here is 1. This is this multiplicative identity, and this forms a commutative ring with unity. Similarly, you can consider set of all rationals under usual addition and multiplication, and C set of all complex number addition and multiplication. These are all commutative ring with unity. And we have Z. This is also a ring. Z is a set of all integers, usual addition and multiplication. This form again commutative ring with unity, and this is also a ring, but it is not commutative. But even though it contains the identity element, multiplicative identity or unity. In section 5.2, we will discuss what is the formal definition of a determinant. So first of all, we define determinant function. In order to define determinant function, we will first define n linear functional on set of all n by n matrices. This is the definition. Let K be a commutative ring with unity or with identity, n a positive integer, and let D be a function which assigns to each n by n matrix A over K a scalar D of A in K. That means we consider a set of all matrices, n by n matrices, that is Mn over a ring K. This K can be a set of all reals, complex is a set of all integers, etc. So we define a function from this to K. Define a function K, and we denote that as D. This assigns D of A belongs to this M and K, a number in K, say some D in K. So this is a function D, and this D is said to be n linear function. D is n linear if it satisfies this condition. Okay, that means it satisfies the linearity of the ith row when the other n minus 1 rows are kept fixed. That means if you consider, even though this the domain of D is M and K, we consider D as a function of the rows of this A. So alpha 1, alpha 2. So D of A can be considered as a function on the rows of A, alpha 1, alpha 2, etc., alpha n. Where this A is defined using these rows, alpha 1, alpha 2, etc., alpha n is the rows of A. So this is the way we consider this map D. And if we fix the first row, and if we fix all rows but the first one, then we can get the linearity. That means if you replace this alpha 1 by C times alpha 1 plus alpha 1 prime, and rest of them are same, alpha 2, etc., alpha n, then you can get the linearity here. So this D can be, this value can be written as C times D of alpha 1, alpha 2, etc., alpha n plus D of alpha 1 prime, etc., alpha n. So if D satisfies this condition, we can say that D is linear at the first row, and if this is true for every row, we can say that D is n-linear. Okay, so D is if you replace alpha 1 etc. C times alpha I plus alpha I prime. If you replace this ith row of this matrix by keeping other rows are fixed, then we can get the linearity alpha I plus 1 etc. alpha n. Then you can write this as C times D of alpha 1 etc. alpha I etc. alpha n plus D of alpha 1 etc. alpha I prime etc. alpha n. If D satisfies this condition for every I is equal to 1 2 3 etc. n, then this D is called n-linear function. Okay, so a function D from mnk to k is said to be n-linear, then that D should satisfy this condition. For example, consider M2R, and we call a general element of this as A11, A12, A21, A22. This is an arbitrary element of this M2R. Then define a map D of A is equal to A11 times A21. So we define this as a map from for any arbitrary matrix A belongs to M2R, the value is this, and this belongs to R itself. Okay, so this defines a map from M2R to R. Now we can verify the linearity of D. D of, if I replace this row A11, A12, this is the first row. I replace this by C times this plus A11 prime A12 prime. This is the corresponding row. If we denote this row as alpha I, and if we denote this as alpha 1, and this can be treated as alpha 1 prime, and this is one row, and the second row is A21 and A22. So this is the replacement of this row, and you can consider this as D of when you add this, you can get A11 plus A11 prime is the first entry of the first row, and second entry is A12, C times A12 plus A12 prime. This is the first row of the entire matrix, and the second row is kept as same. This is A22, and this is equal to by definition. So this is D of the first entry is A11 plus A11 prime, and this will be C A12 plus A12 prime, and this is A21 and A22. So by definition, the value of this D of this matrix is A21 times or C times, or you can write it as C times A11 plus A11 prime times A21. Then you can write it as C times A21 A11 plus A21 A11 prime. But this is C times D of the matrix A11 A12 A21 A22 and plus, and this is nothing but D of A11 prime A12 prime A21 A22. When you evaluate this using the definition, you can get the product of these two, A11 prime times A21. So that constitutes this term, and the D value of this is nothing but A11 times A21, that constitutes this times. Then we have C here. So you can say that D of this quantity, this can be written as C times D of alpha 1 alpha 2. If you write this, this is the alpha 1 first row, and this is alpha 2, and this is D of alpha 1 alpha 2 plus D of this is alpha 1 prime, and alpha 1 prime is we denote this this a11 prime, a2 a12 prime as alpha 1 prime. Then you can write this alpha 1 prime comma alpha 2. Okay. Similarly, you can prove that if you replace this the second row alpha 2, if you replace this second row by C times alpha 2 plus alpha 2 prime, you can get the same thing. So this is one of the examples for the n-linear linear function. So n-linear function defined on M2R. The general cases discussed in example 1. If we consider a positive integers k1, k2, kn, where 1 less than or equal to ki less than or equal to n, and define d of a as a times a1 k1 into a1 a2 k2 etc an kn. So this is nothing but the product of one entry from first row and second entry other entry from the second row and one entry from nth row etc. The product this is the product of such entries. So in this case, in our example, this example is one of the typical cases of this one, by taking k1 as 1 and k2 as 1. So we will choose a11 and a21. Okay, so this is an interesting example, typical case of this example 1. So this is the general case. This form a n-linear function. If you replace one of the rows by keeping others are fixed, you can get the linearity in that row. So this D defines a n-linear function on M n k. In example 2, the classification of a set of four linear n-linear function on M2K can be treated. So this if D is a n-linear function on M2K for any K to K, and this D is n-linear, then we classify all such n-linear function. Because if you consider an arbitrary matrix A, this is 2 by 2, then we write it as A11, A12, A21, A22. Then you can write this matrix if we set epsilon 1 is equal to 1 0 and epsilon 2 is equal to 0 1. We can express this row alpha 1 is the first row, that can be written as a11 a12, and this is nothing but a11 times epsilon 1 plus a12 times epsilon 2. The similar fashion you can write alpha 2 is a21 a22, so that can be written as a21 epsilon 1 plus a22 epsilon 2. Now this d of a can be written as d of alpha 1 alpha 2. So this d is treated as a function on the rows of A. So that can be replaced by d of this alpha 1 can be replaced by a11 epsilon 1 plus a12 epsilon 2, and alpha 2 can be replaced by a21 epsilon 1 plus a22 epsilon 2. Okay, so this is the general expression for alpha 1 and alpha 2 in terms of this rows of identity matrix, because this I is identity matrix is epsilon 1 epsilon 2. So any matrix can be rows of any matrix can be considered as a combination of rows of identity matrix. So that is the idea here. So we can write it as, since this D is n-linear, you can use the linearity in each of the rows. Then first of all we consider this is the row, and this is a constant or this fixed row, and we can apply the linearity on the first row. So you can get a11 d of a11 epsilon 1 comma a21 epsilon 1 plus a22 epsilon 2 plus d of a12 epsilon 2 comma a21 epsilon 1 plus a22 epsilon 2. We applied the linearity on the first row by keeping the second row as a constant, okay, or fixed by keeping second row fixed. So now you write it as a11 d of epsilon 1 comma a21 epsilon 1 plus a22 epsilon 2 plus a12 d of epsilon 2 comma a21 epsilon 1 plus a22 epsilon 2. Now you apply the linearity of this d in the second row, okay. So that is a11 times, we can write this as d of epsilon 1 comma a21 epsilon 1 plus d of epsilon 1 comma a22 epsilon 2, okay. So this is the linearity in the second row. Then the second term will be a12 d of this times d of epsilon 2 a21 epsilon 1 plus d of epsilon 2 a22 epsilon 2, okay. Now you write this is equal to a11 you multiply you can take this a21 out, then a11 into a21 d of epsilon 1 epsilon 1 plus this can be written as a11 times this a22 can be taken out, then a22 d of epsilon 1 epsilon 2 plus from this you can take this a21 out, then a12 a21 d of epsilon 2 epsilon 1 plus from this you can take a22 out, then this is a12 a22 d of epsilon 2 epsilon 2, okay. So this shows that d of any arbitrary matrix can be written as the d value, the sum of the d values of or linear combination of the d values of epsilon 1 epsilon 1 epsilon 1 epsilon 2 epsilon 2 epsilon 1 epsilon 2 epsilon 2, okay. So this shows that using the rows of the identity matrix epsilon 1 and epsilon 2 we can classify all or we can determine the value of d of a using this. That means d of a can be written as a11 a21 a11 a21 times d of epsilon 1 epsilon 1. So once you know this d of epsilon 1 epsilon 1 and d of epsilon 1 epsilon 2 d of epsilon 2 epsilon 1 and d of epsilon 2 epsilon 2, you can get the value of d of a using these entries, okay. This is you can determine the all this is true for any n linear function d defined on this, okay. This is discussed in example 8. This is the classification of linear n linear function on M2K. In lemma we can prove that a linear combination of n linear functions is n linear, okay. So that is because if you consider two n linear functions d and e defined on M and K, then AD plus BE, we will prove that this is again a linear functional n linear functional, that is we consider this as AD plus BE of C alpha I plus alpha I prime. Actually this is the in fact we write this instead of this C alpha I plus alpha I prime, we need to write alpha 1 etc. The ith row is changed as this C alpha I plus alpha I prime comma alpha I plus 1 etc etc n alpha n. So we will neglect these rows or these symbols because we are not doing anything with this these alpha 1 alpha 2 and these rows, because we are considering only the variable row is ith row, so we are not bothering about the other rows. So on the other hand, you can write this as the matrix instead of this one, so that doesn't make any sense. So we can write it as AD plus BE of this is equal to this one. So this shows that this AD plus BE is also a n linear function.